Okay, thank you. Good morning. So let me remind you that yesterday we talked about some principles of paraconsistent logic, what the negation is, what do we expect from paraconsistent logic, apart of being non-explosive, expressivity, having a decent proof theory, etc., etc. And we discussed some ways of reducing multi-valued logics, and some specific, specifically important three-valued and four-valued logics. But as I emphasized yesterday, all of these logics are monotonic. However, human thinking is non-monotonic. Common sense reasoning is non-monotonic because, as we know, if we discover new facts, we may want to retract all conclusions. Okay? Coming back to the well-known Tweety dilemma, if we the only thing that we know about Tweety is that it is a bird, we tend to jump to the conclusion that it can fly. But if we later learn that it is actually a penguin, then we want to change our mind and conclude that it cannot fly. So what we want to do is not only to be able to handle inconsistent information, but to do this non-monotonically. And argumentation theory is one successful way, I think successful, of course, not very objective, but it's one of the ways of modeling way of reasoning with inconsistent information, and at the same time, the reasoning is non-monotonic. Okay, so let me start by pointing to some recent handbooks that appeared on these subjects. This is a very lively subject with a lot of publications. And this is three of the handbooks that I think summarize quite good the state of the art in argumentation theory. So today I will start with some motivations and an introduction to argumentation theory. Then I will turn to the description of abstract argumentation framework. This is an abstract description of argumentation theory. Basic definition, some entailments that can be defined in this context, and some paraconsistent semantics that can be associated with those abstract argumentation framework. Then I will turn to what is really interesting for me in this context, the logical argumentation framework. So adding logic to the abstract view of argumentation. And then, if time permits, if not, then I will discuss it tomorrow, some instantiation of different approaches toward our logical argumentation framework. In particular, sequent-based argumentation, which is the main approach that I will describe in this course, but there are other ASPIC systems, assumption-based argumentation, and so on. Okay, so as I said, all the paraconsistent formalism defined previously are monotonic, but deductive reasoning should be combined with defeasible reasoning, so the ability to change our mind. And to justify this, let me read a quote about this. Human reasoners do not operate with argument and inferences which allow for absolutely no counterexample. Instead, they typically operate with argument and inferences whose conclusion is true or at least highly plausible in cases where the premises are true and nothing abnormal is going on. The requirement that the conclusion be true in absolutely all situations where the premises are true including highly unlikely situation, is for most practical purposes open. So this is one of the justification for considering non-monotonic reasoning. And so if I quote what is written in Wikipedia about argumentation theory, argumentation theory is an interdisciplinary study of how conclusion can be reached through logical reasoning. It includes the arts and the sciences of civil debate, dialogue, conversation, and persuasion, and it studied the rules of inference, logic, procedural rules in both artificial and real world settings. So, particularly, argumentation is a very broad field, a broad and old subject. I will hardly discuss here historical or philosophical issues. The main reason is that I am not a philosopher, but there are many works on philosophical issues, including studies on Sanskrit philosophy or Talmudic logic in Judaism, etc., etc. What I will do here is mainly a description of formal interpretation argumentation methods used in practice in computer science and AI. Okay, so why to use argumentation for me? So there are several reasons for using argumentation. First of all, it's a useful method for combining paraconsistency and non-monotonicity. Secondly, it provides means of visualization, so we can, in fact, see what is going wrong. So it's a graph-based representations of the sources of inconsistency, uncertainty, conflict, etc. Because eventually argumentation deals with argument, counter-argument, and the relation between them. And this is represented by graphs. So if we analyze those graphs, we can pinpoint to the sources of inconsistency and try to handle them properly. And there are many AI-related applications to argumentation theory, which is also a benefit in the field of argument mining, analysis of clinical evidence in medical system, agent-based negotiations over the web, and so forth and so on. Let me just show you one example of a successful application of argumentation-based theory. This is a study done in the University of Dundee on argument mining. As you can see, they can find quite a good big funding here and a few years ago, and this is from I think October last year. So it's quite a successful area. Here they just combine argumentation with machine learning techniques in order to extract argument and counter-argument for different resources on the web. And they are quite successful in doing that. Okay, so let me start with some landmark on modern argumentation theory. There are three, I would say that there are three cornerstones, starting with, in contemporary argumentation, starting with Tullman, John Pollock later on, and P.Dunne, which I will describe their work in a moment. So the Tullman model of reasoning is as follows. So an argument consists of several components. Okay, there is a data, which is the facts or evidence used to prove or justify an argument. Then there is a warrant, reasons or rules or principle why the data warrants the conclusion. The warrant is usually based on some backing, why the warrant can be relied upon and sound, why it is relevant. And then there is a conclusion, of course, proposition making a claim on the acceptance of the audience, and there might be a rebuttal. Okay, so special situation in which the general presumption on which the argument relies is to be set aside. Okay? Let me give you some examples. The first one might be controversial to some of you. Okay, so here is the data. So suppose that Brazil has the strongest combination of offensive and defensive squad among the teams in the football World Cup. Okay, this is that. And since past record in the field of soccer indicates that only teams that is really strong in both offensive and defensive, offense and defense can compete for the championship, then we conclude that Brazil will most probably win the World Cup. Okay, unless, of course, there are some exceptions. Unless, well, one exception could be that Brazil is plagued with injury, or maybe this is an overconfident team, or whatever. Okay, so these are kind of rebuttal for the conclusion that Brazil will win the World Cup. Here is another example for Tillman model of reasoning. It is related to landlord and tenants. So suppose that repairs have been done in the building, and by the tenancy law, all tenants must pay their share of repair to the building they inhabit. Therefore, the rent will be increased unless the landlord has decided to ask for nothing. So this could be one way of overriding this conclusion, despite of the assumptions. In 1995, I suppose, yes, 95, Dunn has proposed an abstract perspective for argumentation theory. This is a well-known paper with many follow-up works. And the main idea is that an argument should be an abstract entity whose role is solely determined by its relation to other arguments. No special attention is paid to the internal structure of argument. And the idea is whether or not a rational agent believes in the statement depends on whether or not the argument supporting this statement can be successfully defended against counter-argument. So the idea is basically very simple. We have argument, we have counter-argument, and the question is whether we can successfully defend an argument against attacks of counter-arguments. That's all. How this is implemented? Well, okay, so I will now describe the abstract view of Dunn by abstract argumentation framework. So I will start with some basic definitions and then continue to the entailment relation that can be defined on top of our abstract argumentation framework. So we have some logic, although the arguments are purely abstract. And then later on, here we will add logical assumptions or a logical framework in order to construct logical arguments. So we first start with the abstract view and then turn to the logical view. Okay, here's a definition, a very simple one. An abstract argumentation framework is just a directed graph. The nodes are arguments, And the arrows are attacks between arguments. So the arrows are represented by a binary relation on the arguments, on the node. Okay, so we say that an argument or a node A attacks a node B if the pair AB is in this relation attack. Let's see a simple example. So suppose that argument A represents the claim that Brazil will win the Mondial. Okay? So note that we don't have any logical structure here. We present this claim only by the argument denoted by A. Okay. Then we have another argument, could be, that says that the team is plagued with injuries. Well, this is kind of argument that attacks A. Okay? Well, now we learn a third argument or a third fact that says still it has the strongest combination of offensive and defensive squads in the World Cup. So now we see that C attacks B. And the interesting thing here is that indirectly C defends A. Okay? By the fact that it attacks the attacker of A, it defends A. And that's the whole idea. Yeah.
So this argumentation scheme is only represented by attacks. If I want to represent a defense, I need to show how an argument attacks another one.
Yes.
Attacks another one that attacks the first, for example.
Okay. So we will formalize it shortly. Okay.
Yeah.
For the time being, we only have a very general and abstract way of representing what is going on. Okay, we have nodes that represent some claims, some arguments, and the only thing that we have is arrows between the nodes. And then we, of course, we should have some graph theoretic analysis in order to understand what argument should be accepted and what argument should be rejected. That's it. Yeah.
It just seems to me that the full graph is the argument. At least from the philosophical point of view.
Yeah.
These they seem more like claims.
Yes.
And I think that is related to these black boxes into the arguments, right?
Mm-hmm.
So it's like, they seem for me more like conclusions. You have black boxes in the nodes, and then you have these.
Exactly, yes. According to the abstract. Later on, we will add logic to it, and then it will be a little bit more complicated or precise.
Okay.
Let's add some notations here. Okay, so we say A plus are all the arguments that A attacks. Okay, for instance, B plus is A, C plus is B. A minus is the set of all the arguments that attacks A. So for instance, A in this graph, A minus is B because B attacks A. And then we can extend it, of course, to sets. So S plus are all the arguments that are attacked by some element in set in S. And S minus are all the arguments that attack some element in the set S. Okay, and of course, S attacks A if there is an element in S that attacks A. So A is in the set S plus. Okay, so in this very simple example, which argument should be accepted? Well, C is not challenged by a counter-argument. There is no attacker on C. Okay? Therefore, we should accept C. We don't have any reason to reject it, according to this simple graph. Now, B is attacked by an accepted argument. So we have a good reason to reject it. Once we accept C, and C attacks B, then we have a good reason to reject B. On the other hand, although B attacks A, the only attacker of A is a rejected argument. Therefore, although A is attacked, we still want to accept it because it is rejected by a rejected argument. So in this very simple case, we would like to accept both C and A. So what we see is that the two primary principles of an acceptance, in order to accept a set of arguments, are one, that all the arguments can stand together, meaning that there are no attacks between the accepted arguments. Okay, we call it conflict freeness. So there are no attacks. The set that S intersection the set that are attacked by S is empty. There are no inner attacks. And the other criteria is that S can stand on its own. This means that any attack on arguments in S is counter-attacked by S. So S can defend its elements. We call this admissibility. We say that S is admissible if it defends all its elements. And also, it should be complete. Yes?
I don't know if you're going to get into that, but we can introduce measure to directed branch.
Yes, I will get it. I will get to it maybe tomorrow, probably tomorrow. Because now I'm only in the basis. But yes, we will add measure. Yes.
Professor, quick question.
Yes.
In this argument graph, could I have a loop of arguments?
Yes. Of course.
Then,
The argument can be there can be cycles. Yeah, we will see in a short moment. Okay. Good question, and we'll consider this. Okay. So an accepted set should be conflict free and it should be admissible. No attack between argument and any argument within any accepted argument should be defended. Okay, what there are the admissible sets in this case? Well, we have in fact three admissible sets. I've already considered C and A because you see that A is defended by C and C is not attacked. Therefore, we can accept both of them. But C is also admissible because it defends itself. It has no attackers. Therefore, vacuously, it defends itself. And also the empty set is admissible here. Okay? Again, because it's obviously conflict free and it defends all its elements. Intuitively, of course, among these three admissible sets, this one looks the most plausible, right? The most interesting. And the reason is that, well, first, it is the biggest set, but moreover, it not only that it defends its elements, but it defends only its elements, exactly its elements. For instance, you see that C defends also A. Therefore, in some sense, this is all admissible, but it is not complete in the sense that there are some elements outside the set that it still defends. So we add the notion of completeness. A complete set should be admissible in the two senses that are shown here, but additionally, it should defend only its argument. Okay, so in this case, we see that the only complete set, I will later call it extension, the only complete set is C and A. Let's consider some more examples. So here we saw that the complete extension is C and A. Yeah.
Excuse me, just a question. Does completeness coincide with maximality?
There might be several complete sets. Not all of them may be maximum. There is I will get into it. There are a subset of the complete set called preferred sets. This corresponds to maximality. So there are several kinds of complete sets.
Yeah, because you would go to maximum,
Yeah.
maximum
Yeah,
consistency.
yeah, of course. Yeah, I will certainly get to this later on. Let's see another example, okay? Now we add an attack from B to C, okay? So what are the complete sets in this case? Well, CA remains a complete set in this case, okay? Because you see that it is admissible, it defends itself, it's not conflict free, and CA and CA defend only themselves. There is no other argument that they defend. But there are other complete sets in this case. For instance, B. B is also complete. Why? It's obviously conflict free because you only have one element here. And it defends itself against all the attack. Okay? You see that C attacks B, but B also attacks C. And the empty set is also complete here. Again, because everything is satisfied with respect to the empty set in this case. Note that in the first case, by the way, the empty set is not complete. Why? Because it is not admissible. The empty set defends C in the first case. Okay? Therefore, the empty set is not admissible in the first case, but in the second case, it is complete. Okay, here is another example. Okay, now we have mutual attacks between A1 and A2, and we also have C and B. What are the complete sets here? So C is one complete set. C and A1 is another complete set. So you see, what are this set is, although it's complete, it contains in another set.
Right.
And we have also C and A2, which is also a complete set.
Sorry. In the first example, then the empty set is admissible but not complete.
No, it is not admissible, therefore it is not complete.
Why is it not admissible?
It is not admissible because sorry, it's not complete. Sorry, you're right. Sorry, it is admissible. It is not complete. Okay, very good point. It is not complete because it not only defends itself, it defends also C. Right. Yes. It is admissible, but it is not complete. Yes. Okay. Let's see what happens with respect to circles. Okay. And here, the interesting thing is that there is a difference between even length circle and odd length circle. Let's see what happens with even length circles. Yes.
Mr. Mister,
Yes.
when we have multiple complete sets, how do we choose? Do we choose at all?
I will come to this at a moment. Okay. We have to choose, and there are several ways of choosing among complete sets. Okay. So, as I said, when we have circles, there is a difference between even length circles and odd length. So let's start with even length. So we see here that with even length circles, we have two options. Let's take of course, circle of size 4 for the moment. Okay, so the status of the arguments are alternating. Okay, or start with A. Okay, if we accept A, then we should reject B because it is attacked by A, by an accepted argument. Then we should accept C because it is attacked by a rejected argument. And then we should reject D because C is accepted. Okay? And similarly, if we start with a rejection of A, then we get the other option. So we have two complete extensions in this case, AC and BD. When we have odd cycles, the situation becomes more complicated. Let's see what happens with odd cycles. So odd length cycles, let's see what happens. So it appears that no argument belongs to a complete extension. In this case, the only complete extension is empty. Let's see why. Suppose that A is accepted, okay? Then we must reject B. But now what happens with respect to C? If C cannot be accepted, because if C is accepted, the accepted set of elements is not conflict-free. There is an attack between two accepted elements. So C cannot be accepted. But on the other hand, C cannot be rejected as well. Why? Because if C is rejected, A is not admissible anymore. Okay? Because it doesn't defend itself against the attack from a rejected argument. Therefore, we conclude that no argument can be an element of a complete extension in this case. So eventually what we see is that we have a three-valued semantics in this case. The green nodes may be associated with accepted arguments, so they may be assigned the value true. The red nodes are out, false, because they are rejected. But there is also a third situation in which an element is not accepted and not rejected, as in the last case. So we have none. So we have actually three-valued interpretations in order to analyze what is going on with respect to complete extension. Okay, in fact, an accepted element, an argument is accepted if all its attackers are rejected. Okay, there is no reason, there is no subtle attack against an accepted element. An argument is rejected if there is at least one good attack against it. So if it has at least one accepted attacker. And otherwise, if the two first conditions are not satisfied, an argument is undecided. The status is undecided. Okay, so to summarize what I've done so far, we have complete extensions. Once we are given an argumentation framework, complete extensions should be conflict-free. They should defend all their arguments, and moreover, they should defend only their arguments. And as I noted in the previous slide, we have another way of interpreting the graph by what we call labeling, three-valued labeling. Okay? So either we can take extensions, which are subsets of the set of arguments that satisfy these three conditions, or we can try to label the arguments according to these three properties, in, out, and none, which I described earlier. And accordingly, by this three-valued labeling, we take all the arguments that are assigned in values and consider them as accepted value. And it appears that there is a one-to-one correspondence between labeling and extensions. So if we have a complete extension, then we can construct out of it a complete labeling, in the sense that we can take the element of the complete extensions and label them in, take all the elements that are attacked by this extension and label them out, and label all the other arguments as done. This is a complete labeling. It satisfies all these properties. And vice versa. If L is a complete labeling, then if we take all the in assignment of this labeling, we end up with a complete extension. Okay, let's see another example. So here is a abstract argumentation framework, and it has 3 complete labeling and accordingly 3 complete extensions. One of them is the empty set, which corresponds to a labeling that assigns none to all the arguments. The other one is A. Okay, so A is a complete extension. You can check it here. And the corresponding labeling assigned into A, out to B, because B is attacked by the element of the complete extension. And all the other, you see all the other arguments are assigned none. Note that this is an odd length cycle, so it's not surprising that they are assigned none. And there is a third case, a third complete extension in this case, consisting of B and D. Again, you can check it according to the definition. And the corresponding labeling assigns to B and D the value in, and the other elements that are actually attacked, all the other elements are attacked by either B or D, therefore they are assigned the value out. Okay, now a question about how we choose among the complete extensions. Okay, and here Dunne proposed several ways of choosing what complete extension should be preserved. Okay, so we start with a conflict-free extension. Remember that E, conflict-free means that E doesn't have a conflict inside itself. And we call an extension naive if it's a maximal conflict-free, maximal among the conflict-free subset of argument. Admissible, as I explained earlier, is a conflict-free set that defends itself. So def E is the set that E defends. It is complete if it defends exactly itself. So E is equal to def E. So these are the important extensions. Which one to choose? Well, we have several options. One option is to take the minimal complete extension. This one is called the grounded extension. Minimal with respect to the subset relation. Alternatively, we can take the maximal complete extensions. These extensions are called preferred extensions. Another option is to take what we call stable extensions. Stable extensions are complete extensions that attack all the other arguments. So anything that is not inside the stable extension is attacked. This is another policy. And semi-stable extension is a weakening of the stable extensions, which means that it is a complete and it has maximal range. So it may not be the case that it attacks all the other arguments, but the union of this set and the set that it attacks is maximal. The reason that we define semi-stable extensions is that stable extensions may not exist. In some cases, we may not have stable extensions. There might be not a complete extension that attack everything that is not in the set. And in this case, we use semi-stable, which is a little bit weaker notion. Accordingly, we can have the similar definition with respect to labeling. Okay, so remember that complete extension is a conflict-free extension that where E is equal to the defense set of E. Complete labeling is a three-valued function satisfying the 3 conditions that I explained earlier. But we also have counter definition for all the other options. So grounded extension, remember, this is a minimal complete extension. When we turn to labeling, it should be grounded. So grounded labeling is a complete labeling with minimal number of in-value assignments. Okay? again, preferred extension is a maximal complete extension. In terms of labeling, a preferred labeling is a complete labeling with maximal number of accepted elements. Stable elements, stable extensions are, as I said, those that are attack all the other arguments. And in terms of labeling, it's a complete labeling without non-values. So each argument is either assigned in or out. It's in if inside the stable labeling, and it is extension and out if it is outside the stable extension. And similarly, semi-stable extension is a maximal, is complete extension with minimal non-values. So the non-assignments are minimized. Okay, in this case, again, we see the free extension, complete extension that we described earlier, the anti-set, which is actually the grounded extension because it's the minimal complete extension. Okay, and correspond to the grounded labeling that assign none to all the arguments. We have two preferred extensions. In this case, two maximal complete extension, either A or B and D, because they are incomparable with respect to the subset relation. Okay, and accordingly, we have two preferred labeling. And among these preferred extensions, only one is stable. Okay, you see the BD is stable in the sense that B and D attack the set B and D attack all the other arguments. So we have two in arguments and three out arguments. They should appear, of course, in red. So there are no non-arguments. Okay, and there is a way of moving from extensions to labeling. So there are mappings between extensions and labeling. And they are just, as I said, as I described before, mapping between extension and labeling, and they carry on also not only to the complete extensions and the complete labeling, but they also carry on to the grounded, preferred, and stable and semi-stable extensions. Okay, so if we start with an extension and use this and construct the labeling as I described before, then, for instance, if the original extension is grounded, then the resulting labeling is a grounded label. And also in the other direction, if we start with labeling, which can be either grounded, preferred, stable, semi-stable, and we consider only the arguments that are accepted, then this set must be grounded, preferred, stable, or semi-stable, according to the property of the original label. Some relations and facts about those extensions. So it can be shown that semi-stable extension is, of course, semi-stable extensions, because this is a weakening of the stable of the notion of stable extensions. Stable extensions and as well as semi-stable extensions are particular cases of preferred extensions, as we saw earlier. And on the other hand, we have grounded extensions. Both of them are instances of complete extensions and or labeling. So we can move from extension to labeling. Complete extensions are admissible, and admissible extensions are contradictory. Two interesting facts regarding to this hierarchy is that the grounded extension is always unique. We have only one grounded extension. It could be empty, of course, but anyway, we have one grounded extension. As I said before, stable extensions may not exist. Okay, so far for the definition of abstract argumentation. Now, how we make inferences from an abstract argumentation framework. Okay, so oops. What are the induced entailments? Okay, so for defining the induced entailment, first we should have an argumentation framework, and then we should fix a semantics. We should decide what extensions we prefer. Do we prefer the complete extension, all the complete extensions, maybe only the grounded extension, the preferred one, or etc. Once we decide about the argumentation framework and its semantics, we can define an entailment relation as follows. Okay, so we have actually two kind of entailments in this case. Skeptical one and credulous one. Skeptical one consider all the extensions, okay, that we have chosen, okay? So argument A follows from the argumentation framework according to the skeptical view if it belongs to the intersection of all the extensions of the same type, of the semantic type, okay? And A is a credulous consequence of the argumentation framework if it belongs to at least one of the extensions. Okay? Here is an example. Okay? Suppose that we have here three arguments. The not here is not really a not, it's not just a strange way of writing the name of the argument because we don't have a logic yet, right? So we don't have a negation. So it's just for the sake of the presentation, okay? Because they attack themselves, they attack each other, therefore I call this not A. So in this case, what we can see, suppose that we take the grounded extension, okay? Okay, no, sorry. If we take the grounded extension, so the only extension here is B. B is the single grounded extension in this case because it's not attacked by any other argument. So it's accepted. Preferred stable and semi-stable extensions are two sets. We either take A and B or not A and B. So we have two extensions once we consider either preferred stable or semi-stable extensions. So in this case, what we see is that according to all the semantics, all the doing semantics, and according to all the type of entailment, whether it's skeptical or credulous, we can conclude B here, which is quite reasonable, right? Because B is not attacked by any other argument. However, again, according to all the semantics and the skeptical entailment, we cannot infer A and we cannot infer not A. Why? For instance, because E does not belong to the intersection of the extensions, not in the grounded case and not in the other cases. Okay? So you see that intuitively, skeptical entailment correspond in some sense to preferentials, to paraconsistent semantics. Because we want to exclude A and not A, we want to exclude the inconsistent part of the framework, but still, despite the inconsistency here, we still want to infer B. And this is what is really happening in this case. Okay, so skeptical entailments are paraconsistent in nature.
But this is also true for classical logic. So if you cannot infer A and you cannot infer not A, it would also be true for classical.
In classical logic, if you have all these three arguments, so we have three arguments, A, not A, and B, okay? In classical logic, of course, we can infer everything because you have the conflicting, despite of the conflict, because of the conflict, okay? But we see that if we adopt the argumentation-based entailments, then there is a distinction between the role of B and the role of the other argument.
Yeah, so if you want to see A, not A and B as true, then you could infer in classical logic. Okay, I see.
This again, this is still, as I said, it's an intuitive way of seeing what is happening. I will make it more formal later. Okay. Okay. So, question?
Yeah,
Yeah.
just real quick. So I have the impression that can you go back to
Yeah.
like, I have the impression that A and not A are being ruled out. And so
Yes.
it seems to me that this is behaving very classically. Yeah. There's a contradiction there, so we're going to ignore it and just consider B.
But if you replace this entailment by classical entailment, then you can infer A and not A, right? In terms of entailment, the conclusions are not classical in that sense. Okay? Here, the intuitive conclusion, although we have three assumptions, okay? One say A, the other source say not A, and the third one say B. Okay, so we get all the information. And we have a set of information which is inconsistent. Again, I call it not A, but for the sake of the demonstration, this is what is happening. Okay, we have an inconsistent set of information
Yes.
coming from different sources.
Yes.
What we do now, according to classical logic, if we accept, based on this, on what we have, we cannot conclude anything. Oh, sorry, so anything meaningful. Okay, we can conclude everything. By argumentation-based entailment, they say, well, okay, this should be excluded. What?
Is it right to say that in this scenario, neither by the skeptical nor by the credulous entailment, neither A nor not A are concluded, and only B is concluded?
No. By the credulous entailment, A is inferred. Okay, there is a difference. Because according to credulous entailment, we take A is inferred if it is in some extension.
Okay.
And according to the, let's say the preferred extension, okay? According to the preferred extension, we can, and the credulous entailment, we can infer A here.
And what is the star in AF?
It's just, you can replace the star by either the skeptical or the credulous. Okay?
Thank you.
Okay. Okay, let me say one word about how we can cope with inconsistency in terms of semantics. So what I call paraconsistent semantics. So very quickly about some extensions to Doom-based semantics. So Doom semantics, as I said, is free value. We either accept something or reject it, or it is undecided. One idea is to relax it a little bit, to say, okay, we do accept contradictions inside the extensions, and still we want to cope with them somehow. For this, we need to switch to four-value semantics. Okay, so now we have actually four states in which an argument can be. It can be either accepted, rejected, or undecided, as in the standard Doom semantics, but it also be controversial in some sense. It is attacked by an accepted argument. Okay? The counterpart in terms of extensions is that extensions may not be complete. So we still want that they will be admissible in the sense that every argument should be defended against attacks. But there might be cases in which the extensions is not complete. The benefits here is that by switching to four-value semantics, we are guaranteed that there will not be an empty extension. We always have non-empty extensions, and this approach is a conservative extension of the conflict-free approach. So any extensions according to Dunne will still be an extension according to the four-valued enhancement. Okay, so in terms of extension, and extension can be is paraconsistently admissible, P admissible for sure. If it defends its element, and it P complete, paraconsistently complete if it defends exactly its element. So the only difference with respect to Dunne semantics is that we relax the conflict-free requirement. And accordingly, once we switch to four-valued labeling, we have, instead of 3 conditions, we have 4 conditions, which are a little bit more complicated, conditions for each situation. When an argument should be in, out, both, or not. Again, we have a correspondence, a mapping between extensions and labeling in this case. Okay, so we can start with an extension and construct a 4-valued labeling out of it. How? By the 4 possibilities. Okay, so if we have an argument, it can be either in the set, but it is not attacked by the set. In this case, it is in. It can be outside the set as well as attacked by the set, and therefore it is out. Can be in the set and attacked by the set, because we are in the 4 values context, then it is both. And they can be outside the set and also not attacked by the set. In this case, we don't have any information about it, and then it is assigned the value none. And vice versa. Once we start with an extension, we can construct a labeling out of it. Okay? If you start with a labeling, we can construct an extension out of it. How? We just take the extension that we take consists of all the arguments that are signed either in or both. Remember that this corresponds to the designated element in the 4-valued case. Remember that top and true were the designated elements in FDE, in the Dunn-Dunlap logic, 4-valued logic that I have described yesterday. So there is a correspondence in terms of labeling. And again, we have a mapping between P-complete, paraconsistent complete extensions and paraconsistent complete labeling. So according to this definition, we can start with an extension and end up with a complete extension and end up with a complete labeling, and vice versa. We can start with a complete labeling and end up with a P-complete extension, and those translations are bijection, as we can see in the last item. And in fact, what I noted earlier is proven here that the 4-valued extension or the 4-valued semantics is an extension of the 3-valued semantics, because if we consider both free labeling, meaning that labeling without the contradictory assignments, then we can get the standard 3-valued labeling. Okay, so if we start with a P-complete labeling without both assignment, then we have a complete extension. So we can just remove the P here, the paraconsistent notation. And similarly for in the other direction. Okay, as you can see here in the 4 itemized way. And these go on also as before to grounded, preferred, semi-stable, and stable extensions. The relations are preserved. Okay, so for instance, let's take this case, okay? E is a preferred extension of the AF if it is induced by both three P-complete labeling of AF with maximal in value, because we consider preferred extension. Okay, so this is summarized in this figure. So the black part of the figure is the one that I showed earlier, stable extensions or semi-stable extensions, which are preferred extensions, which are complete extensions. And once we turn to four-value labeling, we can add those red text, which and we see a full correspondence between the notions. Here is an example. Okay, so here we have an argumentation framework with, and these are all the 16 possibilities of assigning each argument one of the four options. So these are all the possible labelings in this case, and you can see that four of them are P-complete, paraconsistent complete, including the quite degenerated one. It is the last one, which assigns both to all the argument, but it's still P-complete. If you want to switch to complete labeling, then we have three of them. Out of the four labelings in this case are complete. Then two of them are stable and preferred. So AC and BD in this case are preferred or stable extensions of labeling in this case. Okay, another thing that I want to show you is that these extensions or these labeling can be automatically computed. So we can construct theories and compute their models, and the models of the theory show us what should be the complete, the grounded, or the preferred labeling of the framework. That this can be computed. How we do this? So what we do is we are given an extension. We want to represent it by the Dunne-Belknap logic, FDE, together with L'Ottaviano da Costa implication. So this time I point to the correct paper from, okay, you cannot see here it's from the 1970, the correct paper that introduces the implication. And now we can compute using Dunne-Belknap logic, four-valued logic, we can compute the extensions with the following theory. So what is the language? For each argument, we assign a special propositional variable, and we use the connectives of the extended Dunne-Belknap logic. Okay, so we have the negation, conjunction, disjunction, implication, and the false gate. And now how we represent the situation. So we can express by a specific formula the status of each argument. Okay, so for instance, the formula A means that the argument that corresponds to A is cautiously accepted. Why it is cautiously accepted? Because in order to satisfy A, we must assign it the value T or top. So it's either accepted or controversial. So we call it cautiously accepted. Similarly, cautiously rejected argument is an argument that is assigned false or top. So there are some indications that it is false or should be rejected. And similarly, we can define conflicting, coherence, acceptance, rejections, and undecided. Undecided. Here we use an abbreviation, not psi, by the formula psi implies F. So for instance, what coherent means, the formula that stands behind this abbreviation, coherent A, means that A is coherent. It means that it should not be conflicting. Okay, what is conflicting? Not conflicting means that conflicting A implies F. Okay, because not psi implies F. So conflicting A implies F, and conflicting is actually A and not. So coherent A should be replaced by this formula, and this formula is satisfied by T, F, and tau. So if A is coherent, it should not be assigned tau. Okay, and similarly for the other cases. And now we can use those abbreviations or those formula in order to express the conditions for the labeling. Okay, so you see here that we actually expressed in terms of acceptance, rejections, quotient acceptance, etc., the 4 conditions for the 4 assignments. Okay, and then we can actually represent these conditions in terms of theory. So, for instance, consider this argumentation framework. Okay, what is the formula that expresses the condition that C should be accepted, should be inside this framework? So, what PN means, we should accept the argument if and only if all its attackers, all the y's in x minus are rejected. Okay? In our case, in case of C, we accept C if and only if B is rejected. Okay? Because B is the only attacker of C. So this condition is expressed by this formula. And once we take the union of all these formula, we actually get a theory that represents all the complete extensions of the argumentation framework. So the models of this theory correspond to all the P-complete extensions of the framework. Okay, here is a proposition that shows that there is a one-to-one correspondence between the models of the theory, the complete extensions, and the complete labeling. Okay, so suppose that we have a argumentation framework. So a model of the theory that is induced by this framework, it can be translated to a complete labeling of the framework, which in turn can be translated to a complete extension of the framework. And vice versa. Okay, if you start with complete labeling, it can be translated to a model of the theory, and this can be translated to a complete extension of the framework. Okay, so if you want, for instance, to compute the P-complete labeling of the complete labelings, we just have to take the original theory. If we want to compute, for instance, the stable labeling, remember that the stable labeling means that we want that every argument will be either accepted or rejected. So we take the original theory and add extra conditions that require that for every argument, the arguments should be either accepted or rejected. Okay, note that this theory might not be satisfied in case that there are no stable extensions for the theory, for the framework. As I said, the framework might not have stable extensions. In that case, this theory is not satisfied. Okay, what about the other type of extensions? Yes.
But this is always decided, right? You can
decide, but it's not satisfiable.
Yeah, but I mean, you can decide whether or not it's.
Yes, of course, yes, certainly, yeah. Okay, what happens with the other extensions? So, for instance, the grounded and preferred extensions. This is a bit more tricky. Why? Because in order to compute grounded and preferred extensions, remember that we should take into consideration minimization or maximizations. Remember that the grounded extension is the minimally complete extension, and the preferred extension is a maximally complete extension. And we cannot do it by using just propositional language. So we need to add some extra machinery, and for this, one way of doing this is by adding quantified Boolean formulas. What are quantified Boolean formulas? These are propositional formulae extended with quantifications over propositional variables. So just to demonstrate without giving you the exact definition, so think about this formula, where psi is a propositional formula, and we extend it is extended by the quantifications here. What is the intuitive meaning of this formula? It means that there exists a truth assignment represented by x for x, such that for every truth assignment of y, the formula psi is true. Okay? For instance, the formula for every x psi is abbreviation for the conjunction here of psi, where x is replaced by all the possibilities, by true, false, both, and n. Okay, in this case, this formula is represented by for every x psi. Once we have quantified Boolean formula, we can represent minimization and maximization by those formulas. I will not get into the details here. I will just say that, for instance, min says that any model of this formula, its in assignments is a subset of all the complete assignments of the framework. So it's minimal among the complete assignments of the framework, and similarly for max. And by this formula, we can represent actually grounded labeling and preferred labeling. For instance, for grounded labeling, we require that the labeling will be complete, and we add to it the minimization condition. So once we have this theory, we can actually compute all the grounded, because grounded extension is unique. By the model of this theory is the ground extension of the framework. Similarly, the models of this theory are the preferred labeling or the preferred extensions of the theory. And again, here is a proposition that shows that there is one-to-one correspondence between the models of the theory on one hand, the labeling on the other hand, and the extensions of the framework. Some further references, because there are many ways of computing extensions of argumentation framework by using, for instance, SAT solvers, as I mentioned before, QBF solvers, etc. So there are many papers about this. One of them, this paper provides a QBF-based theory for representing semantics of our abstract argumentation framework. There is a survey of logical theory for standard deep semantics for abstract argumentations, some other computational methods and implementation concerning argumentation framework. So we can, there are many others that most of them are surveyed or mentioned in this paper, and in fact there are competitions among solvers in some test cases to see which one is the best, and so you can check it on the internet and see this. Okay, so now let's, in the short time that remains in this session, let's discuss a little bit logical argumentation framework. So far, argumentation were purely abstract entities. Okay, there were no logics in the representation of an argument. Okay? Now what we want to do is we want to make argument valid ones according to some underlying law. So not only we have a framework, we also fixed a logic according to which we want to make arguments. Because now argument is a structured entity. Okay, so now what is the definition of arguments according to the new approach? The original definition, I think it was by Philip Bernard and Anthony Hunter, was the following. So suppose that we have background knowledge, so we have a set of assumptions which is denoted by S. An argument is a pair, gamma and psi, where gamma is a subset of our assumption, a minimal consistent subset of our assumptions that implies, according to classical logic, the conclusion. Okay, so we are actually, and every argument consists of a support set, the gamma, which is a subset of our knowledge base. And if this set is minimal and consistent in terms of entailment, classical entailments, then psi is the conclusion of the argument. And the set of all the arguments is denoted by this. Note that according to the original definition, we take classical logic as the underlying logic of the framework. But we can lift some of the restrictions here. For instance, well, there are some restrictions. Well, first of all, the set should be propositional in the propositional language of classical logic. We have minimality condition, consistency conditions, and of course the entailment should be made according to classical logic. But all these definitions of restrictions of an argument are in some sense not necessary. Okay, we can extend argument to arbitrary languages, not only classical logic but any effectively computable logic. The support set of an argument should not be minimal, and it should not be consistent.
Sorry.
Yeah.
By minimal, you mean that if you drop something from gamma, it stops entailing.
Yeah, exactly.
Right. Okay.
Exactly. So it's only the thing that is really necessary, that are really necessary for the derivation. Okay, so first of all, we can extend it by adding any Tarskian logic. Okay, remember the definition of Tarskian logic. Then we can switch classical logic in our framework by any Tarskian logic, any propositional logic. Secondly, the language need not be the classical, the language of classical logic. Okay. Defined as we remember from yesterday. We can add modalities. We can add other kinds of connectives like in LFI, etc. Why not? Why should we? So this can be a part of our framework. Again, minimality. Again, it's not really necessary because, well, in mathematics, need not be minimal. Okay, minimality may not be even desirable if you consider majority vote. Then we want to consider repetitions. Okay, and sometimes, for instance, in this case, we may prefer the assumption P and Q for inferring P or not Q, because this is a stronger assumption than inferring only P or only Q. This is not a minimal assumption, but it is stronger. Also, why to assume that the support is consistent? First of all, we know that paraconsistent logic properly handling inconsistency. we shouldn't be worried about. Moreover, if we enforce minimality and consistency, this involves some considerable computational considerations. To check minimality and consistency, you know that this is computationally demanding. So eventually what we really want, what really matters for our argument is two things. The conclusion should logically follow from the support, otherwise it's not a valid argument, and there should be an effective way to compute arguments. Okay? So arguments are syntactical objects that should be effectively computable, and they should be refutable. They should be challenged. Okay? And one way, since the only thing that we want is logical validity and effective way to constructing arguments, then something that pops our minds immediately is the notion of sequence from proof theory. Because sequence are just expressions that require that the assumptions will entail the conclusions. Nothing else. Okay? So we may adopt a proof theoretic view of arguments. Okay, so once we have a logic, we can define sequence on this logic, which means sequence are just expressions of the form gamma implies delta, where gamma and delta are finite sets in the language, and the double arrow is not in the language, it's something outside the language. And then we can define an argument. What is an argument? It's just a sequence, gamma, double arrow, psi, where the only requirement now is that psi would follow from gamma according to the underlying logic. That's all. This is an argument, a valid argument. That's it. When we have set of assumptions, the argument, of course, should be S-based. So an argument, you have a single conclusion sequence, an argument, where the assumption should be subset of S. So S defines the outer world of the frame. Okay, so gamma is called in the context of argumentation the support, psi is the conclusion of the argument, and this is the way that we denote all the set of S-based arguments according to the. Here is a simple example. So if we take, for instance, classical logic, and we assume this set, P, not P, and Q, then we have several, well, we can derive many arguments like P implies P, P and Q imply, PQ implies P and Q, and many other arguments according to classical logic. Very simple. How we construct the arguments? Well, we have a way of doing that. Once the logic has a sound and complete sequence calculus, we can use this calculus in order to construct arguments. Okay, so now arguments are not arbitrary entities, as in the abstract argumentation framework, but we can actually produce them based on our logic using sequence calculus. Okay, so we have in sequence calculus we have inference rules that says how we can construct new arguments out of existing arguments. So we have a set of conditions, and by this condition we can construct a new argument in our framework. For instance, here is the well-known sequence calculus from classical logic, LK, which shows how we can actually introduce in the left-hand side or in the right-hand side of an argument each one of the connectors. Okay, so, oops. Yes, okay, so as you know, we have for each connective in the language, we have a special inference rule showing how we can introduce this connective in the right-hand side of the sequence, like like here, and in the left-hand side of the sequence, like in this case, in the case of the conjunction. And of course, we can derive arguments like with trees in LK. So here is, for instance, an example how we can derive an argument that is based on, for instance, the Morgan law, one of the Morgan law. So it's trees that start with the axiom of the sequence, and then it propagates down the tree. We actually start with the leaves, propagate back to the root of the tree, and in the root of the tree is the derived argument of our system. Okay, and so there is a very simple way of producing arguments. How we construct attacks among arguments. So now we have to add new rules, in not only inference rules, but we have to add attack rules for making attacks among arguments. Okay, so we have to introduce rules for the case where the first component attacks the last component in the conditions, and as a consequence, the attacker is eliminated. Okay, so we have inference rule for producing the argument, and attack rules for producing attacks among arguments. Okay, here is one case of such an attack. For instance, here's an attack that is called in the literature undercut. What undercut means? So here we have the attacker, here we have the attack rules. Okay, both of them are arguments. Okay, in what case we would like to say that the first argument attacks the last argument according to undercut? Well, according to argument, if the conclusion of the attacker is logically equivalent to the negation of some support of the attacked argument, then the first argument attacks the other argument. Okay, you see that the conclusion here equivalent to a subset of the support of the attacked argument. And then we have undercut. Here is an example, okay? So for instance, if we have this, again, this setting, P not PQ and classical logic. So one of the arguments that we can construct here is not P implies not P. And this argument attacks, according to undercut, the argument P implies P. Why? Because the conclusion of the attacker is equivalent to the negation of the support of the attacker. Of course, there is a counterattack from P implies P to not P implies not P. And in this case, for instance, not P implies not P also attacks another arguments, PQ implies PQ. Because again, the conclusion of the attacker is equivalent to some subset of the support of the attacker. And we have many other attacks rules. I will consider them tomorrow. What I would like to say for the time being is to show you what is the outcome of all of this. So remember that we had an abstract argumentation framework that consists of abstract argument and attacks among the arguments. What we do when we want to turn to logical argumentations, we use the same structure, okay? The same structure, argument and attack among arguments, but this time the arguments are sequence, okay? And the attacks between arguments are constructed according to attack rules, okay? So just to show you a final example, if we go back to our running example, so suppose we have P not PQ, okay? So we can construct many arguments that are based on this set. And if we have undercut, we can construct the argumentation framework that is induced by this attack rule. Okay, so again, you see, for instance, that not P implies not P attacks P implies P, and conversely. P attacks P, P implies P attacks not P implies not. And we end up with a logical argumentation framework, which is just as an abstract argumentation framework, but now arguments are sequence. And now that we have this structure, we can apply Dung semantics. We can compute here the grounded extension, the preferred extension, and we can incorporate the entailment relations that we defined for abstract argumentation framework. Okay? So now we have a new framework which is logically based. On this framework, we can do all the technique that we apply all the techniques that we used to do in abstract argumentation, consider all the complete, grounded, extension, etc. Extensions, compute the entailment, and then we will see what are the property that the entailment, the nice property that the entailments that are induced by this framework have. So in particular, we see that they are paraconsistent, they are non-monotonic, and many other interesting things concerning the entailment relations that can be defined from this logical argumentation. Yes.
Question. Usually in some sequent calculi for invalidities, for example, when we have the sequent arrow crossed, we interpret that an argument is invalid, right? But this is not the correct reading here.
Right.
Here, the correct reading would be that the argument is unsound or something like that.
It's not exactly, well, this is, in some other context, it could be misleading. It means that it is attacked. So in some sense, we should treat it cautiously. Okay, it's not unsound, it is sound. All the arguments are sound with respect to the underlying logic, in the sense that the conclusion classically follows according to the,
Yes.
okay? The conclusion follows from the assumption for all the arguments. We don't have unsound arguments, but arguments can attack other arguments.
Yeah, I was saying unsound in the sense of valid, but not with true premises.
Exactly.
So that was
Exactly. And so a hint for what will become, if you remember, for instance, for the course of Professor Battens on adaptive logic, remember that you could derive something, but then you can, once that it is derived, it can still be retracted, right? Because it's not finally derived. I hope that I'm using the same terminology that he used. Okay, this is the similar thing happens here. We can derive arguments, but in light of other arguments, we may not accept it, although it is sound inference.
Yes.
Present sound inference.
Yes. So if we
But
have
I will say more about this later. Yeah.
yes.
Yeah.
So each representation is synchronic, right? And if I want to see the diachronic evolution of the argumentation, for example, this is one time exclusively. So the next one, maybe I will have a different configuration of the sets of attacks.
Well, this framework is fixed by several things. One is the logic. Okay, the logic determines what will be the argument. Second, the attack rule. You have to decide what would be the attack rule. The attack rule induces the attack relations. Okay, I presented only one attack rules, but there are many. Okay, so once you fix the set of assumptions, okay, the logic and the attack rule, you end up with a framework. Okay, we have a framework. Okay, now you want to analyze this framework. For analyzing this framework, you use Dung semantics. You decide which argument you want to accept, and based on this, you make inferences. That's the idea.
Is there a theoretic framework for the four values?
Yes, there are some interesting game theoretic approaches. I mentioned the surveys paper. In the survey paper, they mentioned also game theoretic approaches. So indeed, yeah. But I will not talk about this. But there are several.
Yeah. So I don't sorry, I don't understand the meaning of P fly P attacking non-P. Because like, what does it mean?
What I meant before is that the soundness of P implies Q in the sense that we know that it is valid. If we additionally accept that it is sound in the sense that it has true premises, then this undermines the idea of not P implies not P being sound as well. So if the first argument has true premises, the second argument does not.
Well, the meaning is okay. Let me add to what he said. The meaning is the following. Both of these statements are sound. Okay, if you believe P, then you can conclude P, and if you believe not P, you can conclude not P. So, according to the underlying logic, both of these sequences are valid arguments. Okay, but they cannot stand together. Okay, because if you believe P, you conclude P, but your conclusion then contradicts the assumption of the other argument. Therefore, there is an attack from this argument to that argument. Okay? You cannot have both arguments, although both of them are valid, you cannot have both of them simultaneously if you want to avoid contradictions, to have sound reasoning. Okay? That's the meaning of the attack. So they challenge each other. Okay? Let's see another example. For instance, you see here, according to classical logic, here is a tautological sequence. Okay? We always accept it because so you see that it doesn't have any attackers because it's tautological. On the other hand, it does attack this sequence, which is based on contradiction. Okay, classically, this sequence is sound. Right? If you believe classically, if you believe P and not P, you may infer not Q. This is sound. Perfectly okay according to classical logic. But it is attacked by another argument which says, well, your support here is problematic. This is the meaning of the attack relations. Questions? Okay, thank you.